Yo, what up, Seth? All right, I was thinking about yesterday when you asked me about entropy, and it reminded me of an example I did with dice. I just couldn't remember exactly how to phrase it, but I was looking over some notes, and I pretty much have a very simple explanation of entropy for a beginner or someone who doesn't understand it. After all my analyzing, okay, so entropy, we have to just take that it's defined as this guy right here. That's the Boltzmann constant, the natural log, and then this is the omega, which is the grand canonical ensemble function. It's like a partition function. That doesn't really matter. That just means the number of possible states that a system can be in is a function of n, v, and e, where n is the number of particles in the system, or items, or independent entities, whatever. V is the volume, and e is the energy of that system. So each system, when we take the differences in entropy, it's going to be sub 2 and sub 1 means state 2 and state 1. That means if it's a spontaneous thing, it'll be greater than 0. So state 2 will be greater than state 1. That'll be coincide with the positive delta S in entropy, which is good. A negative, a decrease in entropy is not favorable, but possible if you do work on the system. That's beside the point. Now here's a simple example for dice. Okay, I wrote down for dice, we have 2 die, okay? And here's the state that the die are in. So the state is just the sum of the 2 dice. So the 2 dice can either be 2, 3, 4, 5, 6, all the way up to 12, right? The lowest it can be is 1 plus 1, that's 2. The highest it can be is 6 plus 6, that's 12, and then everything in between. And then the number of possible permutations of that state, which means the number of possible different ways you can be in the same energy states. For instance, 1 plus 1 equals 2. You can only do that with a 1 and a 1 on each dice. You can't have one die saying 0 and the other one saying 2 or something. Do you know what I mean? It's a 6-sided die, 2 6-sided die. Now to get 3, it's a little different, right? You can have 1 plus 2 or 2 plus 1. Similarly, all the way down 4, 5, blah, 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 blah. So for 4, we can have 1 plus 3, that's 4. 2 plus 2, that's each dice has a 2 on it. That's 4, and 3 plus 1 is 4. So there's 3 possible states. So overall, when you look at all these states, there's a total 36 total outcomes of the 2 dice that you roll. These are all the die rolls you have. These are the total number of outcomes you can have. This is every possibility without the die rolling on an edge and not being a number, for instance, right? So the highest probability is going to be the 7, rolling a 7, because there's the most ways to get a 7, right? Which there's 6 ways to get a 7. So if you add all these up, you're going to get 36, and then it's a probability thing. Like, what's the probability of rolling a 2? There's one way to exemplify this state, so 1 out of 36 chance. For instance, the 7, the most common die roll, there's 6 ways to get a 7, so that's a 6 out of 36 chance, or 1 in 6 chance. It's a much higher probability to get a 7 than snake eyes, you know what I mean? Or 12. So if state 2, I'm saying the energy function omega sub 1 of state 2, which means getting a 2 on the die, is proportional. It doesn't equal, now this is without going into mad thermo, it's proportional to 1, the number of total permutations of that state. And now we're taking the degeneracy not into account, because 1 plus 2 and 2 plus 1 is not the same thing, because the dice are distinguishable. Meaning we could tell the difference between 1 plus 2 and 2 plus 1. If we didn't know which dice was which, those would be equivalent. But that's different. We can talk about it later. So state 2 was 1, right? So getting a sum of 2, there's only one way to get that. Each die has a 1. That's a 1 proportional to 1. So now, and then omega sub 2 of 7, to roll a sum of a 7, there's 6 ways to get a 7. So that partition function is proportional to 6. So if we want to calculate the change in entropy delta S, which is always greater than 0, of a system going from, the likelihood of it going from state 1 to 2, or transferring from a low entropy state to a higher entropy state, it would be the natural log of state 2 over state 1, which was, remember, state 2 is proportional to 1. All right? So that would give us a natural log of a positive number. I mean, the natural log of a number greater than 1. 6 over 1 is greater than 1, which is delta, and natural logs of anything greater than 1 is positive. That'll give you a positive entropy. So if this was going from state 1 to 2, or state 2, which was a 7, to state 1, which is less likely, we would flip these, right? So it would be, instead of omega 2 over omega 1 would be omega 1 over omega 2, which would be 1 over 6. The natural log of a number less than 1, it can't be less than 0, it's between 0 and 1 and greater than 1. A natural log of a number less than 1 is negative, which corresponds to a decrease in disorder, which is not spontaneous. You could make a system do that by putting work into the system, but we could talk about that. But pretty simplistic terms, entropy is, this is like on Boltzmann's grades, S equals Boltzmann constant K sub B. The natural log, it's actually W on Boltzmann's grade, but whatever. W is the number of ways or the total permutations a certain microstate can be in to be at that same energy level. So these are all equivalent. It's assumed that to get a 7, a 1 plus a 6, and a 4 plus a 3, and a 3 plus a 4, blah, 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 those are all equivalent. Not taking degeneracy into account, very simplified. That's how they define entropy, and that's pretty much it. Let me know.